Okay, let's see if this one will work. Yes, so what I was going to say, I wanted to say it on record for those who might be watching later. I'm still hopeful that maybe they will be watching later. Yes, so the only real class is next Wednesday, and that will be, I won't be here, unfortunately. It will be Tintin, we'll be doing collision detection. That's the last thing I sort of we had to cover. And then there is the final project presentation the next week, yes. So you should submit everything, and you will be coordinating it. He already posted who is in which day. We'll split the teams in half. Some of them will be presenting on Monday, some of them on Wednesday. Then we will grade everything and call it a day. Yeah, so everything is due next Monday. Is that okay? That's what we said before, right? Okay. Any questions on the organizational matters? Or can we go? Oh. It's always much harder to sneak in a class which is like empty, right? Okay, so today we'll talk about skinning. Sometimes people also call it rigging. Did you do so? You were at DreamWorks, right? Did you do any rigging? That's always a big part in production, right? I have a slide about it. So what is it about? It's skinning, not to be confused with like taking skin of animals. This is just an algorithm to compute shape deformation of a 3D mesh. And doesn't even have to be like a single mesh. You can have like multiple meshes, right? Sometimes people would use separate mesh for the eyes or separate pieces for the clothes. So you want to deform all of it in some intuitive way. So it's closely related to what some people call rigging, which means creating this control structure, like sort of imagine like a puppeteer controlling the character. The other way you can look at it, this is the step that happens before animation. So this stuff is used a lot in the industry, both in the computer graphics industries, which I mean games and film. And the way it usually works is that you have specialized artists or technical directors called riggers, and they create these rigs. And what a rig is essentially like a digital puppet. And then they ship it to animators, and animators create beautiful animations using the rig. So sometimes they have to iterate on that. Maybe you can correct me if you know that better from hands-on experience at DreamWorks. Sometimes they need to iterate on it because the animator says, well, I would like this to move, and it doesn't move in the rig, then they have to go back to the rig. And the same thing is relevant in both film and games. The difference being that in games you are much stricter in terms of performance. But even in a film, you always need this interactive. And interactive means something between 15 to 30 milliseconds. Maybe you can go a little bit higher, but then you're already pushing in. Why does it matter for film? Because in theory, in film, you can be spending days or even months to render it, right? But this matters because the animators, when they are creating the performance, well, they have to have the rig moving, right? That's also one of the reasons why physics, and here is sort of like a classification of skinning methods, physics-based skinning has been explored, but hasn't been used all that much in industry. I think it's slowly but surely changing. There are tools like, I think the best is Beta Tissue. That's the system they are using at Weta Digital in New Zealand. That's what they first deployed at Avatar. So it's not here because these are just academic papers. But their stuff is definitely based on these research results. So they first used the physics-based skinning thing on Avatar, and since then I think they've been using it on like Lord of the Rings and The Hobbit to create these really nice muscle effects and the dynamics and so on. There's stuff I don't know much about it because it's not public. They only had like one talk at SIGGRAPH 2010, which I've been to. Even that talk wasn't recorded, so like it's only like what you remember from the talk. What I remember is that they were saying that the physics-based rigging was incredibly slow. So what they did, they had to bake it into post-space deformation. They essentially had to approximate the physics with something faster so the animators could actually work with it. So yeah, the physics is, it gets you the nicest effects, but also the slowest thing out there. Here is one interesting way how to speed up physics. We won't be talking about this because it's sort of a specialized topic, but it's one important idea how to speed up physics is to do subspace physics or reduced order physics. Do you know what that is? It means running the simulation in a low-dimensional linear subspace. So usually when we were talking about deformable solids, we had some state vector x, right? And I was saying that it has dimension 3m, where m was the number of particles, or the degrees of freedom of your FEM discretization. Well, the idea is if you have a deformable solid, then this is an overkill, right? Because you cannot expect that it will create all sorts of crazy high frequency deformations, right? What you can do is to create a low dimensional linear subspace and restrict the simulation to it, and that way you can get it much faster, but it still won't be as fast as the data-driven or geometric techniques. Those are the fastest skinning techniques out there. And those are definitely the most popular in games. That's all you could do. And even in film, people like to use that a lot just because it's so easy to use, it's fast. And it's also simple. So we will start with that, and eventually we will get to the connections to physics-based things. So people didn't used to be thinking about the standard skinning problem as something physics-based, but I think that's wrong because it's intimately related to elasticity and quasi-statics. That's what we talked about before. But let me give you first the traditional skinning overview. So the simple skinning algorithm you can think about is called linear blend skinning, and many other algorithms derive from that. And here is how it works. You get a character. Oh, this is, by the way, how I got into seriously interested in graphics research. So today I will be mostly talking about my work, actually, with some exceptions. Yeah, because this is my favorite topic. This is how I got into it. I was really, really excited about how to take a character like this and make it move around, right? Do something nice. And back in the day when this started being developed, like maybe 20 years ago, and actually Norm Badler, he did some pioneering work in this area. You wouldn't even, it would be a joke to think about physics-based simulation of like the anatomies and everything, right? So these techniques were developed. So, okay, so what is the basic setup for skinning? So we have a polygon mesh, you all know this, right? So it has some vertices. So I will describe it, for example, on how to deform this vertex. Every vertex deforms independently, so we can just pick one and look at what happens there. So the first thing is we have the rest pose with the vertices. The second thing we need are bone transformations. So that's where the rig comes in. We'll not be talking in detail about the skeleton, but you have an intuitive idea what a skeleton is. It's a tree of rigid transformation. So it's the same model you would be using in robotics for robots, right? Rigid links connected at joints. It turns out for skinning, it doesn't really matter the fact that the rigid bodies are connected at joints, because they can be even completely disconnected, and I will take advantage of that in a second, and all this stuff will still work, okay? So what we do need for skinning are bone transformations for all the bones. So for example, I need to have a transformation which tells me where the forearm bone maps from the rest pose to the current animated pose. And this animated pose is changing in time as the character is dancing around whatever she's doing. So this is M1 for the forearm bone, M2 for the upper arm bone, and so on for all the remaining bones in the body. So you have as many transformations as you have bones. And again, the bone doesn't really have to be like a physical bone, right? You know that the forearm doesn't even have a bone. Like there are two bones, radius and ulna, right? So it's actually more complicated than this. So the bones are really just an abstraction, or they're our handles, if you will, to control the deformations of the character. So that's number two. First was the rest pose. Number two is bone transformations. And number three are vertex weights. The vertex weights, they connect the rest pose with the skinning transformation. They essentially put the two together. So what the weights are, they are scalar functions defined on the polygon mesh. And they range typically between 0 to 1. So 0 means zero influence, and 1 means maximum influence. The vertices with influence 1 will directly follow that particular bone. So here is a weight for the forearm bone. So the vertices here, they will be perfectly following that transformation. And the vertices between 0 and 1, they will be sort of blending. They will be blending with the remaining weights. So this is the vertex I was talking about. We've got a weight W1. It should be something about 0.5 here, right? Because it's right in the middle. And we have another weight for the upper arm bone, and so on. We would have a weight for all the bones in our body. So here, our vertex here would get a different weight, W2. Again, would be something like 0.5, right? And the most basic skinning algorithm and the most standard skinning algorithm, you'll find it in many games and everywhere, is called linear blend skinning. And what linear blend skinning does, it does a logical thing with this setup, right? What you would do to compute the deformation is blend the affine transformations together using the skinning weight W as the blending coefficients. Let's see if I can do this fancy thing here. Highlighter. No? That's pretty shitty. Never mind. So you do a linear combination of the transformations. You will get a matrix out of that.
Shouldn't this weight be normalized for each vertex?
That's a great question. Yes. Usually you assume that the weights sum to 1. Yes. Usually you assume that they are non-negative and that they sum to 1. Correct. And that's how you get a translation invariance there. Correct. Yes. That's the usual assumption. Yes. And what this does, it maps the rest pose vertex to the deformed pose. And then you can do something for the normals. It's a little bit trickier for the normals if you want to be mapping normals, or you can just recompute the normals. And here the n is the number of bone transformations have to be blending together. So in simple cases like here, we would have only 2, but in some more complicated areas like the shoulders, for example, there you typically need to blend more. So the bound of the number of non-zero weights, as you saw on the picture before, right? The weights are like pretty localized, right? They're almost always 0. Only in small area they are non-zero. And the bound of the maximum number of non-zero weights per vertex is typically 4, because that goes well with graphics hardware, right? Because 4 is a good number there.
How many weights would there typically be?
As many, you have 1 weight for each bone, right? So as many bones, that many weights. So for a character, you can get away. Simple character can have like 20 or even 15 transformations. If you go all the way to production, you can have 1,000 production level rates. Okay, so linear blend skinning is a linear mapping. So here's the first fun thing we can do about it. So first we can write it in matrix form. So we can create this matrix W, which this is basically just rewriting this in matrix form. I did this in detail in my skinning course last year, SIGGRAPH. So if you want to go into math, you can study this. And then there are some other linear skinning techniques, but I don't want to go into that detail now. So the matrix W is just a matrix which combines the rest pose and the skinning weights in some funny way. Okay? But it's going to be a constant matrix in the sense it does not depend on the pose. So this is the matrix W, and the TP, those are the affine bone transformations, affine transformations stacked into one long column vector TP. Okay? And that the P is the pose, so this vector does depend on the pose. As the character dances around, this T will be changing. And what we get from it, just matrix vector multiplication, we get VP, and those are exactly the deformed vertices according to linear blend skinning. So because linear blend skinning is linear, you can write it as a matrix vector product. Any transformation that's linear, you better be able to write it as a matrix vector product, right? And what's my point here? My point is that we can use this to do a more interesting way of creating these skinning parameters. Because how do you typically, where do you get the skinning weights, the bone transformations, and the rest pose? Well, typically you do that in a tool like Maya, right? Some of you have done it. Or maybe most of you have done it, right? It was the class. No? I thought this was the guy. Scott, yeah. Who's teaching this. And that's what you need to be able to do if you want to work as a rigger in a company. And these guys are really good at it. They can do that very quickly. If you are not good at it, like myself, then you spend days and it's not going to look any good. But you basically have this nice user interface and some sort of like weight painting tools, and you can edit them and make them smooth and all sorts of cool tweaks, and then the riggers know their tricks around it. But one thing I was exploring, and I guess that's now a very popular thing to do, to be learning from data. So one thing I was investigating is if we have some input data, for example, output of a physics-based simulator, so some simple physics-based simulation like this cloth flapping in the wind, it turns out that you can take this animation and extract skinning parameters out of it. So even though this is not something you would immediately think would be suitable for skinning, right, because it's a flag, you don't really see any obvious skeletal structure or anything like this, it turns out you can actually skin that. You can convert it to linear blend skinning. And why would you want to do that? They like to do that a lot in games, because if you have first of all, you cannot afford the phys-based simulation at runtime. You just don't have the budget for it. They just did on your game, they didn't give you the budget for it. So what you're going to do, you're going to compute it offline, right? But then it generates tons of data, right? All the vertex positions for every frame, that's too much data. They don't give you budget for that much memory, right? Welcome to the games world. So what you're going to do, you have to compress it. But then you have to compress it in a clever way so that when it's being decompressed, it can be rendered very quickly because you still have this very little budget, right? So if you did some fancy compression technique, you would be screwed when decompressing it. So what you can do here is to approximate it with linear blend skinning, and that's going to be cool. Because if you do that, then you can use the same routines as the skinning is using for characters. So you actually don't even need like extra decompression code. You can sort of piggyback on the routines that are already there in the engine, if that makes sense. I hope so. And the way how you can do it, because you can write skinning as matrix vector multiplication, it turns out this is related to matrix decomposition. Specifically sparse matrix decomposition. Because if I give you frames of an animation, so this is the first frame of the flag, second frame of the flag, and so on for whatever frames of the flag I have. And then, oh, maybe I should not be going away because that won't be recorded. And the W is the matrix that combines the rest pose and the skinning weights. Wait, what did I just say? I just said it wrong, right? The frames are V1 to Vm. That's the input. And the T1 to Tm are the bone transformations I'm looking for. I don't know them. I have to find them. So that's why I made this blue. Oh, I need to figure out a better pointing thing. That's why I denoted it in blue font, because those are the unknowns we'll be solving for. Okay? So the V1 to Vm is the matrix of input frames. Somebody gave it to me, probably a physics-based simulator or some motion capture thing or whatever. And I want to write it as linear blend skinning, as W times T, where T is the matrix T1 to Tm stacking the bone transformations. Okay? So you might have seen this before. I would hope you have seen this before, where these waves that mean approximately, that the product of W and T should be as close as possible to V in some metric, or that metric being typically Frobenius metric. So if I ask for W and T to be low rank, what problem do I have here? Or what is the solution to it? If all I'm asking for, the W and T are matrices, right? They must have the right dimension, so I can multiply them together. And if I just want W and T, if I tell you, here is a matrix V, find me W and T such that I can multiply them together and they are low rank. Low rank means that they have, so the W has a small number of columns and T has a small number of rows, so I'm getting compression, so I'm saving data. So if I'm asking for low rank, the solution is very well known. I'm sure you know it. Huh? It's a different type of decomposition. It is definitely a matrix decomposition problem, because we have an input matrix V, and we also to tease apart the two parts, right? To make it even more interesting, the story, the W is essentially the spatial part, because the weights vary spatially over the surface of your character, or whatever or flag, or what have you. And the T varies in time as the animation. So it's like a spatial temporal decomposition if you want to make it more dramatic. So if I'm asking for SVD, exactly, as simple as SVD, yes. If all I was asking for was they are low rank, that truncated SVD gives me the optimal answer. So with skinning, it's a little bit more interesting, because in skinning, the problem looks the same, but we have a little bit different requirements on W. We have more strict requirements on W. What requirements do we have? We have requirements that each weight needs to be localized. Okay. So that's the thing with SVD. If you ever played with SVD PCA, the thing you will get that the modes are global. They affect everything, right? But it's not such a nice thing to work with, right? Imagine you are an animator and you want to move the hand, but it moves everything else a little bit, right? Not so cool, right? Because then you have to be compensating for everything else, and that's not good. The other reason why do we want these localized and sparse weights is for efficiency purposes, right? You have the limit that every vertex can have at most 4 transformations affecting it, right? So if you don't have this locality, then you have to do much more computations, right? If you have like 50 bones, then you have to do 50 arithmetic operations as opposed to 4. And more importantly, you have to also fetch more data from the memory. So that's why there's many good reasons why you want this sparsity in skinning. And that leads to a little bit more tricky optimization problem. So now you want to find the decomposition W and T, subject to the constraint that W should be sparse and non-negative. And I tried a bunch of things to solve this. And what turned out to work very well is alternating optimization. It's exactly the same thing we talked about last week, right, about the fast mass springs. I did this before, and the fast mass springs came later, but it was essentially the similar idea applied in a completely different context. So the idea here is that you first fix W. After you have fixed W, then W becomes black, and you are only solving for T. Well, that's a linearly sparse problem, right? We know how to do that. Now, if you fix T and solving for W, well, then the constraints on the locality and non-negativity kick in. So it boils down to a quadratic programming problem. I'm not going to go into details because I could easily spend the whole lecture just on that. If you want more details, it's in my Eurographics 2010 paper. And then you iterate these 2 steps. And just like in projective dynamics, aka fast mass springs, this converges really well. So here is an example. How does it work on the flag animation? That's the same flag I showed you before. So here every color corresponds to 1 bone transformation or 1 weight, and this is just some initialization. I'm not even trying to be particularly clever on the initialization. I did just some region growing clustering or something like this. Actually, I think this was one of the projects which I was proposing to figure out a better initialization for this. Anyway, this is just an initialization, and then we run the alternation for the flag sequence, and this is what it does. So the weights start overlapping up to the maximum of 4 overlaps per each vertex. Here is how it converges on 1 example frame. And here are the final weights it learned. So you can see an interesting thing. The weights sort of picked up the shape of the wrinkles. And here is the result. So this is what you are looking at is skinning with 32 bones and carefully optimizing bone transformations and weights. So do you think it looks like the same, or do you think it looks different? Some people actually told me that they can spot some differences, which I have a hard time noticing. And there are a little bit differences from the original, but other than that, it's quite close, I would say. And this is using 32 bones. And as I said, the cool thing about this is that you can use the same routines for skinning the cloth, that's what we are doing here, as you are using for skinning the character. So here I did a cloak using 35 bones, and the skirt needed a little bit more bones because it has intricate wrinkles. It will also work with less bones, but then it wouldn't look as good. So that's one interesting thing you can do with skinning. Okay?
Would this be controllable in here? Would this be controllable or editable in here?
If it's editable? That's a very good question. I mean, you certainly can go in and edit it, but it won't be as intuitive as having a rig, right? Because now the transformations are just sort of floating in space and they don't have any structure. The skeleton is nice because it gives you this nice hierarchical FK structure, right? Like if I move the shoulder, it moves the whole thing. You could definitely do something. There was a little bit of research in this direction, but not enough. I could easily imagine like a research paper doing exactly what you proposed, which would be very, very interesting. There was, by the way, some more recent research in this direction trying to improve these algorithms further and further. Okay, so the next problem of skinning I would like to tell you about, because that's my most best known work. There are these problems called candy wrapper artifacts. Because with large rotations, I might have mentioned it before, right, at some point, but I never told you the solution, right, to Quaternion skinning. So that's what I'm going to do now. So you have these candy-wrapper artifacts, which it's a known thing that all linear techniques have some limitations. Because when we have to deal with large nonlinearities, for example, due to large rotation, that's what's going on here, right? We have a large rotation compared to the rest pose. The linear technique does not handle it so well. It essentially collapses the skin, which does not look very natural. So the cool way you can think about it is from a geometric perspective. So all the bone transformations are rigid body transformations. So that means that they are points on SE3. Did we talk about SE3, the special Euclidean group in 3 dimensions? Okay. So just long story short, it's a group of all 3D rigid body transformations, and it's an example of a Lie group, which means it's not just an algebraic structure, but also a geometric structure. It's a smooth manifold. Specifically, it's a 6-dimensional manifold living in 12-dimensional Euclidean space. Why 6-dimensional? We definitely had this before, because we are talking again about rigid bodies, right? This is also relevant in rigid body physics, by the way. Translation and rotation. Translation in 3D space, 3 degrees of freedom. Rotation, another 3 degrees of freedom, right? So it's a 6-dimensional manifold, and lives in 12-dimensional Euclidean space. Well, why 12-dimensional? Because by default you represent it using matrices, right? And how many degrees of freedom the matrices have in 3D for a rigid body transformation. Well, you have the linear part, that's a 3x3 matrix for the rotation, and then you have 3 degrees of freedom for the translation, right? So 3 and 9 is 12. So I don't know how to draw 6D manifolds in 12D, so I decided to just draw an ellipse in 2D, just to give an intuition. But actually, it works quite well for the intuition. So what linear blend skinning does, if I give it 2 transformation, M1 and M2, for example, the forearm bone and the upper arm bone, what linear blend skinning does, it just does linear blending between them, right? Which means straight shot from M1 to M2, somewhere in between, depending on the skinning weights, you will get the result, right? But as you can see on this illustration, if you do this, you will leave the SE3 manifold. The SE3 manifold is curved. It's some sort of spherish. It's a little more complicated than a sphere, but it's definitely not flat. Okay, so the M-blend, the blended matrix, is not going to be a rigid transformation matrix. The translation is always going to be a translation, but the linear part of the transformation won't be a rotation anymore. You will get this scaling and shearing side effects, and that's exactly what's causing the candy wrapper problems. In especially bad case is if the relative transformation between M1 and M2 contains 180 degrees rotation. Because in this case, you are actually passing through a singular matrix. Let me show you what does it mean in practice. So this is like my bending bar example with 2 bones. And I'll do linear blend skinning, and I will be twisting the second bone about its own axis, okay? And this is what it does. So once I get to 180 degrees rotation, the middle cross-section collapsed exactly to a point, which means it was being transformed by a singular matrix, right? Everything squished to a single point. So that's the extreme candy wrapper artifact. And this is what you get on characters, so it does not look so good. So how would we solve it, right? Like from this geometric perspective, it's sort of obvious how you would solve it, right? You want to respect the geometry of the SE3 manifold, right? You want to stay on the manifold. You don't want to leave it. And this is called intrinsic blending techniques. So that means instead of measuring Euclidean distance in the 12-dimensional embedding space, you want to be measuring geodesic distance, which is restricted to the manifold itself. Have you heard it before? If not, you certainly will in some contexts. It comes up in all sorts of different contexts too. So here we would be blending the geodesic distances on the SE3 manifold. If you are guessing this will get much more complicated, you are completely right. But this has been investigated quite a bit before. By the way, this Kumar guy, that's Vijay Kumar, who's the new Dean of Engineering. I always wanted to talk to him about this work, but never get a chance.
He's a very nice guy.
I know, but also very busy. he was in DC all this before, so I never had a chance to actually meet him. But this is a slate of algorithms for doing exactly this, the manifold intrinsic blending. And if you do that, that indeed solves or you can never have problems. But the problem is it gets much slower because the mathematics get more complicated. But what's worse, you will end up doing you will end up with some optimization problem. And that's a big, it's significantly slower than linear blend skinning. As linear blend skinning, you're just doing linear combinations of matrices, whereas here you end up with some nonlinear crazy optimization problem which you have to be solving with some gradient descent or Newton's method. And it just gets much slower. So in industry, people never really adopted these techniques. Just because you could get a little bit better deformations, but they just could not just justify that it would get much slower. So my idea was to use dual quaternions for this problem. And the cool thing about dual quaternions is that they let you do a closed form approximation of the SE3 blending. So you can have a nice, very efficient closed form expressions which get you something which is not as good as the ground manifold intrinsic blending, but it gets very close. It's definitely much better than doing linear combinations of matrices. So what are dual quaternions? Dual quaternions are a generalization of regular quaternions, right? And that's what we already talked about. One of the few lectures. I told you even the bridge story, right? Remember that? So those are regular quaternions. And dual quaternions, they were discovered 30 years later, also in the 19th century, by another genius mathematician called William Kingdon Clifford. If you heard about Clifford algebras, then dual quaternions are actually a special case of Clifford algebras. Some people also call it geometric algebras with like a little bit different flavor to it. Some physicists are using that a lot. So how do we generalize from quaternions to dual quaternions? We put there this dual unit. This is this magical at thing. So you can think about the at as in quaternions you have the I, j, k, the imaginary units. So the at is going to be a new imaginary unit. It's going to be a different type of imaginary unit because before the ijk squared, they always gave you -1, right? The at square is going to give you 0. So it's sort of weird. It's even algebraically weird because it creates some sort of weird, like non-zero divided by 0, some weird algebraic things. The intuition is certain better. The intuition is that eta, if you have some small number and you square it, you get super small number, right? So the intuition is that this at is a number that is so small that its square just vanishes completely. So maybe it makes sense, maybe not, but just think about it as imaginary unit. And what we can do now is to define a dual quaternion as a sum of two regular quaternions. So it's going to be Q0 and Q at, where the Q at is multiplied by this dual unit at. Okay? And that turns out that gives you a reasonable algebra. It's going to have 8 degrees of freedom, of course, because every quaternion has 4 degrees of freedom, and if you have 2 of them there. That's by the way, why it's called dual quaternion. It's not to be confused with duality or anything like this. I don't know why did they name it this way. I don't think it's the best name, but that's what it's called. And now you can do lots of mathematics with it. Again, I could spell an entire lecture showing you how the things from quaternions generalize to dual quaternions. And it's sort of cool. And again, you can read more about that in my paper. Because pretty much everything from quaternions we can generalize to dual quaternions. And it's sort of cool to work with this dual unit thing. But what we'll need here for skinning is the manifold of unit dual quaternions. So that's what I denote Q1 hat. By the way, I use the hat to denote dual things, to differentiate them, to distinguish them from non-dual things. And so the manifold of unit dual quaternions are dual quaternions which have norm 1. Okay? The norm is a little bit funny here because if you do it in math, you will find out that the norm must be a dual number. So it actually has 2 degrees of freedom. So it's also like 1, 0. It's like complex 1, right? It's also like 1, 0 sort of thing. So because the norm is dual number, the 1 is also dual number, these are actually 2 equations in 1. Okay. So from the original 8 degrees of freedom of a dual quaternion here, after you apply this constraint, you end up with a 6D manifold. Okay. Because you took out 2 degrees of freedom. And so it would be a 6-dimensional manifold living in an 8-dimensional Euclidean space. Okay? And it...
Which 2 degrees of freedom?
these two, the norm of Q equals 1. So the norm of Q is a dual number. So it has a real part and dual part, if you will. The real part must be 1. That's one equality. The dual part must be 0. That's the second equality. So that's what we took out. What does it mean geometrically is a little bit trickier. Let's not go there now. So let me first explain you why the dual quaternions are important. That's because the unit dual quaternions, they exactly represent rigid body transformations, right? What we discussed is that quaternions nicely represent 3D rotations. So dual quaternions generalize it to rigid body transformations, including translation. So I have a little demo, which I've done a long time ago, but it's still good. So here I'm taking a teapot and rotating it about an arbitrary axis in space and describing the quaternion. So these are regular quaternions. Any 3D rotation you can represent using a quaternion. Okay? With dual quaternions, you can also do translation, interestingly. You can see the dual part of the dual quaternion is changing as I'm translating the teapot around. The rotational part is staying constant because I'm not rotating it. And I can, because it's an algebra, it's a beautiful thing, I can multiply the translation and rotation together. And you get a generic screw motion, and that's a general rigid body motion. Yep.
So you basically have a rotation plus a translation.
You have a rotation plus a translation.
That's about it. The dual quaternion.
Yes, that's you can look at it that way. Yes. Yeah. Many people are like this. Like so what, right? Why don't you just have a matrix and a vector, right? That does the same job, right? And indeed, many people, when I submitted my first papers, were like, so what, right? It looks like that this is just a different semantics to represent rigid body transformations, right? Like different weird mathematical way to think about the same thing, right? So there is actually a significant difference to SE3, okay? And the difference is, because you might remember this from regular quaternions. All this stuff applies to regular quaternions as well. There is no isomorphism between the Q1 hat and SE3. And that's because of this, what's called the double cover property. That means that the dual quaternion Q and minus Q represent exactly the same rigid body transformation. Okay, so that's called the double cover of SE3. It's exactly the same property for regular quaternions. Okay, this just generalizes exactly the same thing, but adds the translation in there. Okay, and adds the translation in there in such a way that the double cover property still holds. So let me try to explain this double cover, because that's the key. That's why linear combinations of dual quaternions work better than linear combinations of matrices. That's the only reason how it's different. If you could also just take the rotation part and convert it to quaternion and keep the translation vector around, right? It turns out that would not work, because there you sort of just double cover the rotation and not the translation. You sort of treat them separately. But this thing that treats the rotation and translation in a uniform way, and that works. So let me explain it a little bit better. So if you have our situation on SE3, so let's pick the worst possible case, where the relative transformation between M1 and M2 is the 180 degrees rotation. That's where the linear blending passes through a singularity. That's where we get the worst candy wrapper, okay? And if we look at the same situation on the manifold of unit dual quaternions, if we convert M1 to Q1, that's a unit dual quaternion corresponding to M1, and M2 to Q2, then we find out that now they are all of a sudden much closer together. Okay, so if you do linear blending there, then you are far away from the singularity. You are much closer to the manifold. Okay, so these problems, it's not, you're not exactly doing the intrinsic blending, but you are much closer to it. And that's the consequence of the double cover property. The other way you can look at it is, let's see if I can get the highlighter to work a little bit better. That's so great. The other way you can look at this, if you start here, and if you traverse this full loop, if you do one full loop, what do you have just, let's forget about translation for a second. Let's see with this. You start with this as identity, and if you do one full loop, you did 360 degrees rotation. Okay. If you do the same thing on the manifold of unit dual quaternions, guess what happens? You will get the 360 degrees rotation already here. And if you do the whole loop, you will do 2 revolutions. You will do 720 degrees rotation. Okay. And that's the reason why the dual quaternion blending works better than blending of matrices directly. So what we're going to do, we're going to take the matrices, we're going to convert them to unit dual quaternions, and there is a catch, how to select the signs, right? Because we can pick the signs arbitrarily. We have the conversion routines are not really complicated, it's some simple closed form procedure, but we don't know how to pick the signs, right? The conversion routine gave us some random sign. We could as well pick minus q. So, and this is actually very important to get this right, because what you want to do in skinning, you want to be doing shortest path interpolation, right? If I had a red teapot and my task is to rotate it onto the blue teapot, I can get there two ways. I can do the shorter arc or the longer arc, right? What I want to do in skinning is the shorter arc. I think we talked about this when we talked about slurp. This is exactly the same problem. So if I show the situation in quaternions or dual quaternions, so one would be the unrotated teapot, that would be the reference pose, and the blue rotation I can represent either using q or minus q. Okay, both q and minus q represent exactly the same transformation. After you convert it back to a matrix, no difference. But there is a difference with you when you start interpolating. If you interpolate between 1 and q, you get a different path than if you go from 1 to minus q. Okay? So here, as you can probably guess, if you go between 1 and q, you get the shorter arc rotation. And if you go between 1 and minus q, you get a longer arc rotation. So what you want to often do what you want to always do in skinning is to pick the shorter arc rotation. That's what lots of people get wrong when they are first implementing it, and then they're like, "Oh, what's happening? It's like twisting the arm like too many times," and this is exactly why. So what you need to do is to pick the signs such that the angles are the small ones, not the big ones, which is sort of easy because you just look at the dot product. If the dot product is negative, you flip the sign. Okay, so once you have done that, fix the signs, then you take your blending coefficients. So in skinning, those will be the weights, right? Either provided by your riggers or from some algorithm that compute the weights for you. Then you compute the blended dual quaternion, and then you have to do an important thing, then you have to normalize it. Because you are not too far from the manifold, but you're not exactly on it, okay? But the cool thing about dual quaternions is that the projection back on the manifold is easy to do. It's just 1 over the norm. Yeah, question?
Do you really need dual quaternions? Why don't you just blend translations independent, then rotations independent as normal quaternions, and then just normalize this just normal quaternions?
It's a great question, and it's of course what I tried first before I came up with this. The problem is it doesn't work. There is some subtlety. It's a little bit tricky to explain, but basically, if you do it this way, if you do the quaternion and translation pair, then it depends on what coordinate system the translation is in. By default, on the origin of the coordinate system, and that's where it will be rotating about. Okay, so by default, like the character would probably have somewhere like in the center of mass would be the coordinate system, right? Like somewhere near the pelvis or something. And if you are computing transformations here and rotating about this point, it's gonna do something horrible. That's exactly what it does, something absolutely unacceptable. Unless you make sure that you change your coordinates and translate it to the joint, then this works. But that means you need to have there some logic to sort of worry about the coordinate systems. The beauty of dual quaternions is that this problem disappears, because they are oblivious to what coordinate systems the things were in, because their translations and rotations, they are sort of combined nicely, homogeneously together. These problems don't appear there. So at the end of the day, after you do the normalization to unit dual quaternion, you get a closed form, because this is all closed form. Even the conversions to dual quaternions, the normalization, those are just operations, right? You don't have to be solving any Newton or anything like this. This is just a sequence of instructions. And the result is always a rigid body transformation. Because of the normalization, you project it back onto the manifold of unit dual quaternions, you get a rigid transformation. So what does it mean in practice? If you have these ugly candy wrapper artifacts, and you switch to dual quaternion skinning, you get a much more natural skin deformation, because the shearing, or no, the shrinking is not there. So here is a comparison on the bending bar. One more time, the same thing. So the dual quaternions give you the corkscrew type of deformation. And here is a mock-up clip I took a long time ago in Dublin. Yep.
In terms of double quaternions, can you actually do real like geodesic waste mixing?
You can, yeah. And I have that in my paper too. But again, you will have to iterate on it. I did even a comparison.
Iterate on it?
Yeah.
Why?
Well, nobody knows a closed form algorithm that would compute with the true geodesic. You could do it for 2, sure.
Right, because it's not a sphere anymore.
Correct. Even for a sphere, nobody knows, as far as I know, a general closed form algorithm.
For a sphere, for a sphere, it's not easy.
Weighted averages on sphere for arbitrary number of points. For 2, that's easy, right? But if imagine you have 3 points on a sphere, and you have weights, and you want to do weighted average constraint to the sphere. I don't know of a closed form algorithm to do that. If you do, I'm pretty sure you could write a paper about that. Because the best paper I know that does this is iterative. It converges fairly quickly.
Okay.
So these things about closed form are more quickly becoming moot because the computers are getting faster and faster. But the closed form is good because then you can actually better analyze the algorithm and reason about it, right? Okay, so this is just, that's now in Maya, it's been used in many games and some feature animation. But let's look more into the limitations. So the one problem is where to get the weights, right? Like, because if you have a training animation, then great, then you can run the skinning decomposition, which I talked about earlier. But it's sort of like a chicken and egg problem, right? If you already had an animation of the character, then you probably don't need to rig it anymore. So usually you're just given a rest shape, and you have to create the weights for it. Okay. There has been some relatively recent research on this topic. I guess still the state of the art or the standard point of reference are bounded by harmonic weights by Alec done at CIS563 2011. That's what they do. And if you use it on a character, you really get some fairly nice weights. And the beauty is that these weights are automatic. You get some very good-looking weights, which are nice and smooth. They are localized. They are non-negative. And they are you just compute them with the hit of a button. And computing the volumetric discretization, that's sort of the ugly part. You need a volumetric discretization of that whole thing. But if you are doing physics, you have a volumetric discretization there anyway, so that's not a big deal. The thing is that, so the first problem of skinning, both linear blend skinning and dual quaternion skinning, you have to get the weights somewhere, right? And some weights are easy to compute, some weights are automatic, but maybe they will not give you the ideal deformations. Because some weights can be better than others, okay? There's another limitation. A dual quaternion sometimes can give you this behavior, which some artists didn't like. They told me, how can you fix this sort of bulging artifact? If you do bending of a cylinder like this, then you get this type of behavior, so it sort of bulges out. Some people thought it was a bug, but no, this is really what dual quaternions do. So that's why, like in Maya, there is an option to blend it in with linear blend skinning, so you can sort of suppress this effect. But what I was thinking about was how to remove this problem in a principled way. And the inspiration I took from physics, right? The direct skinning methods essentially mean you have just a formula how to compute the deformations. And what we talked about before, when we talked about quasi-static elasticity, you can also pose it as a variational problem, right? If we have some elastic deformation energy E, and we have some constraints, the constraints are not written here, then you can pose the skinning as variational problems, optimization, minimizing some elastic energy, right? The typical elastic energy people use for this purpose is a Corotated elasticity. Do you still remember it? Then cover this one, right? It's sort of like the finite element analog of a mass spring system, if you will. So here I tried to compute the deformations using Corotated elasticity for the bending cylinder. Okay, so you can see I discretized it with voxel grid. You can see lots of tiny voxels on the cylinder. What I did, I put two constraints in the cylinder. So this is like a poor man's approximation of the upper arm, right, of the upper limb. So there is one bone, another bone, and then I rotate the second bone, and these are the deformations it will give me. So these are very nice deformations. There's no bulging problem, but the problem is that this is now much slower than skinning, right? So we cannot really ship this in a game or something. That would be even worse than the manifold intrinsic blending algorithms. So beautiful results, but way too slow. So what I thought was, well, maybe we can somehow combine these two things. Do a little bit of like geometric skinning or direct methods, and with a little bit of physics. And this led to these elasticity-inspired deformers. It was a SIGGRAPH Asia 2012 paper, and those are the results it produces on the bar. I will show you some better results later in some actual characters. So here is the idea. This is what you should already know, how we do. So this is quasi-static elasticity. So we start with some volumetric discretization. It could be a voxel grid, or it could be a tat mesh. It could be anything. And then we assume that's like a very rough approximation of the human body. We assume that the human body is made of rigid bones, which are just like rigid steel rods inside, which can possibly deform. And the rest is just homogeneous. This is the flesh, or this is a homogeneous elastic material. So the homogeneous elastic material, we've defined the Corotated elastic energy, and we minimize it subject to the constraint that the bones are held in place. Okay, so we prescribe where the bones are, and we minimize the correct energy to get the deformation of the flesh. Here is one, if you don't remember how the Corot elasticity works, here is a very intuitive explanation for the case of a 2D voxel grid. Okay, so if this is your deformed voxel and it started as this rest pose voxel, what Corotated elasticity essentially does, it first finds a best fit rotation. Okay, and then we look at all of the edges. Oh, that's exactly what you were looking at in the FAST paper, by the way. Look, all of the four edges, and we sum their square differences. Okay, the idea is we would like the green edges to be the same as the red edges, right? In that case, then there is no energy, and the more deformed it is, the more energy we want, or we will have there. And this is the formula you will get after some algebraic massage. You might notice that this is very similar energy to what we got with the fast mass springs, right? So this is the same ideas are appearing over and over again with different flavors. I don't know, maybe it's because I don't have any other ideas. And what do we want to do? We take this energy, we put the constraint that some of the vertices are fixed. So now we are talking about vertices inside also. Okay, so some of the vertices correspond to bones, so some of them we freeze, and we minimize the energy over the remaining ones. Okay? And these are the results we get there. So very nice results, but very slow. So what can we do to get similar quality results, but much faster? Something that's fast enough for interactive posing. So let's first consider a simple problem. Let's assume that we are just looking at this cylinder, so that there's just one joint. And let's assume that we are only allowed to linear blend skinning. That can happen to you very easily if you go to work at the game studio. They will tell you, nope, we just used linear blend skinning. And they'll be like, okay, so what is my physics-based class? What was it good for? Well, here is what it was good for. You can be still changing the weights, right? They will not tell you you must use these weights. You can choose whatever weights you want, because what numbers are there for the weights that will not affect performance, right? So what you could do, and that was my first idea, was, well, why don't we try to find the weights such that after we use them in skinning, we get minimal Corotated elastic energy, okay, over a range of poses. So for the cylinder, you can imagine that I have two sample deformations, 0 and 90 degrees, okay? So M1 is the 0 identity rotation, M2 would be 90 degrees rotation. This is the skinning matrix, so MI is the skinning matrix, so M1 is the for identity, M2 is for 90 degrees. And the MIW, that's the matrix vector formula that computes linear blend skinning. Okay? So the VI prime is the deformed pose for the skinning with the MI matrix. And what I want to do is I want to find the weights W such that after I do the skinning, after I compute MIW, my elastic energy, the Corotated energy E, that's what we talked about before, after I sum it all over all the K poses, will be minimized. Okay? So this is an again, I will spare you the details. If you want to see the details, you can look in my SIGGRAPH Asia 2012 paper. I will show you the results though. So if you solve this for the bending cylinder example, for linear blend skinning, you will get weights that look like this. So there certainly is still the candy wrapper problem. But if you compare it to the bounded biharmonic weights, those are the state-of-the-art weights before, you can see that the elastic energy minimizing weights, they give you a little bit more natural deformations, right? That's because the elastic energy is lower here than it's with BBW. How BBW work, they minimize the squared Laplacian, which is also an energy measure, but it does not really measure directly the elasticity. It measures, it's more related to heat diffusion, really. So they give you some nice weights, but these weights are a little bit better. But the problem is, of course, what is ugly is that the candy wrapper is still there, right? But now we know how to get rid of the candy wrapper. We get rid of the candy wrapper by switching to dual quaternion skinning, right? And it turns out that we can repeat the same idea for dual quaternion skinning. It will get a little more complicated because instead of matrix vector multiplication, I have some nonlinear function because the dual quaternion skinning is nonlinear with respect to the weights. Because I'm doing this normalization, and yeah, because of the normalization, that's why. But nevertheless, it will still give me an optimization problem, which I can still solve, even though it's a little more nonlinear, if you will, optimization. But it's still solvable. I just use K-nitro to solve it. And here is the result I got. So those are the optimal skinning weights for dual quaternion skinning and this bending cylinder. So certainly the candy wrapper went away, right? And if we compare this to bounded biharmonic weights with dual quaternion skinning, we again see that the deformations get a little bit more natural because they have lower elastic deformation energy. Lower elastic deformation energy usually means more better looking deformations. But the problem is that this ugly bulging thing is still there. That was bugging me. Like, it's almost, it's hard to see here, but if you compare it to the true quasi-static solution, you can very clearly see there is the bulge is still there, right? And sometimes you don't want the bulge. So how can we get rid of that? So the observation I made is that both linear blend skinning and dual quaternion skinning are essentially oversimplifying the problem because they are rotation invariant. They do not or cannot distinguish between torsion and between bending. They just treat both of them in exactly the same way. Okay, you can sort of interpret it as isotropy, but the term might be a little bit overloading. So what I argued is that we need a little bit different skinning model. It can still be a closed form skinning model, but needs to take this, if you will, anisotropy into account. More specifically, the fact that the torsion deformation will behave differently than the bending one. And that was the idea that led to what I call joint-based deformers. And the idea is, so what is a deformer? So let's think about it. If your job is to explain deformations near one joint, okay, let's focus on one joint. Let's focus on the elbow joint here, okay? So first, if we want to have any chance to be anisotropic, we need to define their coordinate system. Okay? So by convention, we can have the coordinate system point with the z-axis towards the bone. So we know which axis is the bone. And then if you want to describe deformations around this joint, there are spatial deformations, right? Spatial deformations are just mapping from R3 to R3. Okay? And the deformations will depend on the rotation of the joint. Okay, so these mappings are mappings from the rest pose to the deformed pose. That's a deformation field. And this just says that they depend on the rotation of the joint. As the joint is moving, the spatial transformation is changing. And that's the idea of a joint-based deformer. So joint-based deformer is an abstract concept, something that consumes a rotation and a rest position x and gives me a deformed position x prime. Okay? And if we have such a deformer for one joint, then it's sort of easy to put together deformers for all joints. Because all I need to do is to define a blending weight associated with the deformer. And if I have another deformer, for example, shoulder deformer, then I can take another weight, and what I can do is simply blend the deformers together. So it's sort of, if you think about it, it's sort of a generalization of the standard skinning idea. Where in standard skinning, like bone-centric skinning, that's the linear blend skinning and dual quaternion skinning would be examples of the classical transfer or bone-centric skinning. Okay. And there what you were doing, the weights were sort of associated corresponding to bones, right? We had one weight corresponding to the forearm, one weight corresponding to the upper arm, and so on, right? So the blending was happening somewhere in the middle, right? Here is where all the blending was happening, right? And the deformation primitives there were just rigid body transformations, right? In standard, both in dual quaternion skinning and in linear blend skinning. Each bone was just a rigid body transformation, right? So the idea of the joint-based deformers is to essentially make this a little bit more powerful, the concept. So you have these joint-based deformers, which can be more general deformations, and we will still blend them, but we will blend them such that the blending is happening halfway through the limbs, essentially. So the deformer itself is taking care of the complicated deformations near the joints. That's what the deformer's job will be. And then the blending will be just to put together the individual deformers. Okay? Similar ideas have been explored by some other people in the industry. There's a thing from Sony called, offset curve deformation and animation space. If you want to know all this background, that you can go to my skinning tutorial. But okay, so far the joint-based deformers are an abstract concept, right? So far I didn't give you any specific algorithm. So if you think in C++, this is like an abstract class, the joint-based deformer, okay? So what I still owe you is an actual implementation. And one actual implementation which is sort of good is a swing twist deformer. Why is it sort of good? Because I think the swing twist deformer is the simplest deformer which avoids both the linear blend, the candy wrapper artifacts, the linear blend skinning problems, and the dual quaternion bulging problems. Okay, so the swing twist deformer does really well on both bending and twisting. And the idea is really simple. So again, it's a joint-based deformer. So it takes a rotation and a rest post position. And the first thing it does, it decomposes the rotation into a swing and twist components. Okay. I said for convenience, the z-axis is pointing, it's aligned with the bone direction. So the twist means rotation about the bone, about the z-axis here, about the bone direction. And the swing component is the rotation which changes the direction of the z-axis. Okay. It turns out you can do the swing twist decomposition elegantly using quaternions. It's not so difficult to figure that out. There was some old inverse kinematics thesis that also discusses this. It's just a cute thing that you can do this very elegantly using quaternions. You don't have to do any like SVDs or anything complicated. It's actually quite simple. And once you have done this, then what we are going to do, we are going to do spherical blending on the twist and linear blending on the swing. The idea being simple. The idea being that we like how linear blending works on the bending deformations, but we prefer the dual quaternion skinning for the twisting deformation. So we basically combine the two, but we combine them in a nonlinear way, unlike Maya, which combines them in a linear way, right? Okay. So these SNT, the SNT here, those are some auxiliary weights we need for this deformer. So it gets a little bit more complicated. You need some more weights there. But the good thing is that I described how we can automatically compute these weights, right? These weights will be found as the elastic energy minimizing weights, so you can actually find them automatically. You don't have to hire an artist that would paint it for you. So this is just showing that this is an example of the swing weight, and this is an example of the twist weight. Here I am just showing that you don't have to be super careful about how many samples of the rotations do you use there. This is just a subtle point. What's more important is the final algorithm. So how does it work if we put it all together? First, we pre-compute all the weights, the swing and twist weights, and the deformer blending weights. What we used for the deformer blending weights were just BBW, just bounded biharmonic weights. It turns out that they were not so critical, that anything worked fine. And I think that's because there is not so much blending happening between the individual deformers. Because the deformers already take care of the hard stuff, and then the deformer blending is to just smooth the transition from one deformer to another. And so this is all pre-computation. And at runtime, all we do, we evaluate the deformers, and we blend them together. It's really very similar to standard skinning, just that instead of rigid transformations, you're evaluating the deformers and then blending them to work just like in skinning. So the cool thing is that this is fully automatic. You almost don't need a rigger here, even though that's a very over. Riggers would probably disagree. And here are some results. So here is how does it compare to the quasi-static elasticity. That's what the nonlinear elasticity is. Our method, that means the swing twist deformer with the elastic energy minimizing weights. It's not exactly the same. It's the quasi-static elasticity is a little bit better, but our method is way faster than the quasi-static elasticity. And here is a comparison to the previous, I guess, competing techniques. So that's linear band skinning and dual quaternion skinning with bounded biharmonic weights. And you can see that the method I just described avoids both of the candy wrapper artifacts and the dual quaternion bulging artifacts. Even better comparison is here. This is sort of a cool case. So this is a simultaneous bending and twisting of the arm, which is a pretty natural motion. And you can see artifacts with both linear band skinning and dual quaternion skinning, because that's the case where both of them have some problem. The new method, the swing twist deformer, that handles this case beautifully, and this is without any rigor, really. All that is there is a skeleton, and the rest is automatic, minimizing energies to get the weights. So here I was playing a little bit with isolating the artifact. So this is another type of a standard candy wrapper artifact. Here is what I call the bulging artifact of dual quaternions. So sometimes it doesn't look so good. It creates like exaggerated knee. In some cases, actually, artists liked it, like on knuckles of like fingers. They actually liked this bulging behavior. So it's always hard to make everybody happy. But here, with this method, you have control over it, right? You can put anything into the joint-based deformer. So this is what happens with bounded biharmonic weights. The bounded biharmonic weights are a little bit too eager to grab large parts of the mesh. So what happened here, that's because it's essentially heat diffusion. So they don't look at the deformations of the thing. They just look at essentially, simplified way, heat diffusion. And then they end up controlling sometimes too large part of a mesh. And of course, the artifacts can be combined, right? Like here, the bulging behavior of dual quaternions is exacerbated by the overly generous spread of bounded biharmonic weights, if that makes sense. Oh, this is my favorite artifact. I call it the Achilles heel of bounded biharmonic weights. So there is some bulging thing in the middle, but that's not my point here. Look what the heel is doing. Do you see what's happening to the heel? So the heel is getting deformed a lot with bounded biharmonic weights, right? And this is because the bones here is, as you see, there is one bone here, one bone there. So what we essentially do, we heat this bone, right, and let it diffuse. And what BBW end up doing here is making the heel highly deformable, right? Which is not really the natural thing to do. The natural thing to do, and that's what the elastic energy optimizing ways give us, is to concentrate the deformation around the angle region, right? So that's what we get for free. And this is just a demo that I can really, as I said, we can combine all the deformers together by doing these deformer blending weights and put it all together on one body. And if you look carefully, you can notice all of the artifacts I talked about. It's a little more subtle because now you have the whole character. but the artifacts are definitely there. And you would be surprised how meticulous, like in animation studios, they are about like super tiny details. They don't want like a single pixel go wrong, right? A whole, yeah, you can.
Yeah, we actually had exactly a very similar problem that was not solved. On penguins, they had an owl, and owls can turn their heads to 70. And we never figured out how to solve that.
Yeah, that's pretty cool. So this is just saying that the runtime performance is very fast because this is, it doesn't really get too much more complicated than linear blend skinning. You have to evaluate the deformers, but they are just closed form operations, and then the blending is pretty much the same as blending in LBS. You need 2 extra weights, so it's a little extra compute, a little extra memory, but not really too much. It's in the same ballpark. The preprocessing takes a little bit longer. Turns out that the slowest thing is computing the BBWs because you are solving some fairly large quadratic programs, and even with the best solver you found, the Mossack solver, it takes a while. And I think we are still at the very beginning of actually exploring this. There is still many things that need to be done properly. Collisions and contact is one of the big things. And anatomical deformation models. This is something I will show you the work Sanchit has been contributing to. So we talked a lot. This is I'm sort of almost wrapping up the course at this point. So physics-based animation is a fairly mature area in graphics. This has been developed a lot with like people like Ron Fetke and many others. They made lots of contributions, and the effects in movies and games, they are very good now, right? They are still expensive, so that's why visual effects houses are struggling, but that's a little bit different story. On the other hand, biology-based simulation, that hasn't been really explored all that much in graphics. And what we are looking at very recently, what I was always excited about, was mathematical models of growth. Deformation usually has like a little bit negative connotation, right, and skinning too. But I would argue, as in some cases, deformation can be actually beautiful. Some people made their career based on deformation. So this would be an example of hypertrophy, right, which is coveted by bodybuilders. But maybe even more important type of growth is the opposite process, atrophy, right? If you get hurt and you get a cast, then your muscles cannot move and they atrophy. So they shrink, okay? So what we did very recently, this is going to be presented at this year's SIGGRAPH, but I will give you already a preview. I mean, it was conditionally accepted, but hopefully it's accepted finally soon. So we essentially combined muscle models or growth models from biomechanics with physics-based simulation, okay? And it's a model similar to elastoplasticity. We didn't talk about plasticity, but essentially all that means is changing the rest pose. Okay. So what does it mean? This is a deformation gradient from the rest pose. This would be the rest pose, like a little muscle or something. This would be the deformed pose. And what we say here is that the rest pose first grows. Okay. So we have a growth model. You have a growth model, which in this case we just say that the muscle grows perpendicular to the direction of muscle fibers, because that's the model they were using before in biomechanics. If you think about it, it makes sense because the muscle has these fibers in it, and the length has to stay the same, right? Because the bone is not going anywhere, so it can only expand in the direction perpendicular to the muscle fibers. And the remaining part is the elastic component, and that's there to account for the fact that if one muscle grows, it pushes the surrounding muscles out of the way. And that can be explained using elasticity. So we combine these two things together, and we again wanted to make it interactive. And one way, there were two key tricks to achieve interactivity. One was using the projective dynamic solver. That's what we talked about the last class. And the other trick was to carefully design the TAT mesh. So what we did is called a muscle envelope. So if you watch carefully, what I'm doing here is I'm shrinking the skin until it reaches the muscles, until I can't shrink anymore or have it intersect. And then we mesh it in such a way that the muscle envelope is embedded in the mesh, and the muscle envelope creates a clear separation between the subcutaneous fat and the rest of the stuff, the muscles and the fat, and no, not the fat, the inner organs. Okay. And that helped us get an interactive system where we can simulate effects such as this biceps hypertrophy. It's even better visible on this muscle view. And you can notice that the effects of elasticity are still there. As the biceps is growing, it's pushing the chest muscle out of the way. You can sort of notice that there. And as we were playing with this, we also proposed a model for fat growth. So fat is an interesting substance. It's a sort of like a semi-fluid material, okay? And what we ended up doing is using a model that's similar to pressurized rubber balloon model. But it turned out to produce quite appealing body shapes. And another thing we did a tool to change the proportions to increase the size of the bones, the length of the bones and the surrounding flesh. And we put this all together and created a system that lets you generate different types of body shapes, highly muscular ones and tall ones and lean ones, and different types of obesities. This was Sanchit's work, by the way, creating these beautiful obese shapes. And we also tried combining obesity and muscularity, some obese and muscular. Maybe you have more to say because this was your tweaking mostly. Yeah, but the results speak for themselves. So that's the end of this presentation. Thank you for your attention. Yeah, we have still a few minutes if you have some questions. Yeah. Probably do, but
that resizing of bone structure, what allows skinning to maintain its behavior if the bones are stretched?
Oh, that's a great question. Like, we have actually another paper which I didn't talk about this that will be presented at Eurographics 2015. That's with Li Feng Zhu, my postdoc here. That we wanted to do actually, I can show you on the website actually. That we wanted to do exactly that. We want to have a model such that after you change the length of the bones, the skinning will still remain functional. So you have like we call it adaptable anatomical model. I can at least point you to the paper, which is barely published. It's this one, adaptable anatomical models. Oh, sorry. To do this. Talking about this paper. It was like a motion capture paper, but a big part of that was this adaptable model, which has the bones inside. You can rescale the bones, and the skinning still keeps working. So you have to sort of design it carefully so it accepts the stress scaling of the bones. You know. All right. Any other questions?
One more. So when you do joint-based, joint-centric model for skinning, are the joints local in their effect, or would one joint influence, like the solution for one joint affect the solution for another?
Well, what do you mean by solution, right? You still want to have it in a hierarchical chain, of course, right? Yeah. That if you move one, if you move the shoulder, and everything else, it follows that motion.
Right, but two separated hierarchies do not interfere with one another. Right?
What do you mean separated?
The left arm's shoulder would have almost zero influence on the right arm's shoulder.
Correct. The influence of the underlying assumption of the joint-based deformers is that they are really just local to the joint. Yeah, and you're right that this is actually one weakness of this work, which is again ripe for future work. That this is really just scratching the surface, because I actually observed some artifacts due to this. Like in the shoulder, for example, you would probably need to do something slightly more sophisticated than this. As far as I know, it hasn't been done. All right. Anything else? This was sort of like a high-level-ish overview, and you can find the details in the paper, so we can talk about it later if you want. Okay, so let me see if the recording worked. Looks like it